Hello guys, in that part of lecture 5, we're gonna answer two questions. The first one is, if we have a function that is already defined, but it's not defined as a sum of min terms or sum or product of max terms, can we still represent this function as sum of min terms or product of max terms? And the answer is yes, and we will see now how in this lecture, in this part of the lecture. And the second question is, what is the hardware benefit of expressing a function or representing a function as sum of min term or sum of max terms, okay, or in general sum of product or product of sum. Okay, so let's start by the first question. If we have a function, it's already defined, it has some expression, can we convert this expression into sum of product, sum of min term or product of max term? So let's see that by example. So we have here a Boolean function f equal to a plus b prime c. Okay, so and we want to express this function as sum of min terms. Okay, so basically we have two solutions here. We can go in two ways. The first one is using our best friend, the truth table. Okay, so basically here we have three variables, a, b, and c. So we have 8 combinations, and you just, for each combination, you just substitute in the function and you get the corresponding value. For example, when a is 0, b is 0, c is 0, then we have 0, or b prime will be 1, dot 0, so this will be 0, and so on. Okay. Now we look at the ones, because these are the min terms, right? And our function will be just sum of these min terms. So remember the numbers. So this is 0, 1, 2, 3, 4, 5, 6, 7. So basically f is sum of m0, m1, m4, 5, 6, and 7. Okay, m1, m4, m5 is m6 and m7. So f is equal to sum of 1, 4, 5, 6, and 7. Okay, good. So what is the other way to do that? The other way is the way that we usually afraid of or panic, which is the analytical way. Okay, yes, if we just don't have this truth table thing, we can do that analytically as well. Okay, so let's do it. It's a fun actually. So f equal to a or plus b prime c or b bar c. Okay, and we want first we want sum of min terms. So we want something plus something plus something. That's one thing. And also in each term we need the three a product of 3 letters, a and b and c, all the time. Okay, good. So we have here 2 terms actually inside f. Actually f is sum of product, by the sum of product, yeah. So we just convert it, it's already sum of something, so it will be just sum of min terms. That's what we're gonna do now. It's already sum of product, but we just convert this product into a formal form of min terms. Okay, so let's start by a first. So a can be written as follows: a and b plus b prime. Guys, b plus b prime is just 1. A and 1 is a, so we didn't do anything here. So this will be basically ab or plus ab bar. That's very nice. Okay, now we have another literal here, okay, which is b. Okay, now we have from a we get 2 terms. Okay, we get AB and AB bar. I need both of them need to have C in them, right? So basically, we're gonna do that as follows. So we're gonna multiply C plus C prime to the first term, then again C plus C prime to the second term. This will be AB C plus AB C prime plus A B bar C plus A B bar C bar. Okay. Do you have here any repeated term? Let's check. I don't. Yeah, we don't have. Okay. Good. Now the second term B bar C. This is easy. So this will be just multiplied by A or A bar. So this will give us B bar C A plus, let's write it in that way better. I'm sorry. So A B bar C plus A bar B bar C. Okay. So F at the end will be equal to, just write the equivalent of A. So A B C plus A B C bar plus A B bar C plus A B bar C bar, plus the equivalent of A B bar, which is A B bar C plus A bar B bar C. And look for any repeated term before you finish. ABC basically is unique. ABC bar also unique. AB bar C, yeah, this is repeated. So we'll just take one of them because X plus X is equal to X in digital design. So for Boolean algebra, so AB bar C, then AB bar C bar, and yeah, these both are unique. The rest, the two rest terms are just unique. Okay, this is basically sum of product. Okay, but sum of min terms. So it's both sum of product and sum of min terms. This guy here is only SOB, sum of product, but it's not sum of min terms. So let's now find the corresponding min terms of these terms that we get. So ABC is just 111, which is that one here, M7. ABC bar is 110, so this one M6. AB bar C is 101, this one M5. AB bar C bar is 100, which is M4. And finally, A bar B bar C is 001, which is M1. And yes, we have M1, M4, 5, 6, 7, 4, 5, 6, 7. Okay. So this is basically also sum of product, but it's a product of min terms. It's a sum of min terms. The product here are, each product is a min term. Okay. Now let's see, the opposite. If you are given a function, how to represent it as a product of max term. Here is the second example here. F equal to xy plus x bar z. Basically just changes the variables from ABC to xyz, doesn't matter. Okay. And again, we have two solutions. The first one is the analytical, is using truth table. And the second one is also analytical solution. So let's start by simpler, which is basically the truth table. So if we do the truth table for this, it will be something like this. Okay. And now we look at the zeros, not the ones. And these are our max terms. So F equal to. So remember to enumerate the terms that you have. So 0, 1, 2, 3, 4, 5, 6, 7. So F should be a product of M0, M2, M4, and M5. Product of M0, M2, M4, M5. Or you can just write product of 0, 2, 4, 5. Okay. Can we do that analytically? Yes, we can. But it's a little bit more complicated here than the other one, the first one, the first example. Remember the first example, F is already sum of product. We just changed this product to main terms. But here it is sum of product, and we need it to be product of not just a sum, we need it to be a product of max terms. So first we need to convert F into a product of sum, then we convert this product of sum to product of max term. So we need first to convert F into a product of sum, then from product of sum to product of max terms. So that's the basic idea, or the basic steps that we're gonna use. Then whatever you did in the first one, you did here, but in the opposite way. You there you multiply by x plus x bar. Here you multiply, you add x bar. Okay, something in that way. So begin first. We have two terms here. So F equal to xy plus x bar z. That's very simple. Let's use the very very beneficial property, which is the distributive property. So basically you can distribute xy over x bar and z. It's a very unique and very useful property in digital logic for Boolean algebra. So this is basically equal to xy x bar xy or x bar, then xy or z. Okay. Good. Now we use this distributive property again to just reduce this multiplication. We want to, eliminate any multiplication here. Okay, so F equal to, we can distribute x bar over x and y. So this will be equal to x or x and x bar here, or y. Then again, distribute z over y and x. So z over z or y, z or x. This is very useful. You can distribute with the multiplication or even the addition. In decimal, only with the multiplication. Now we have four terms, and generally now the shape of F is a product of sums. This is basically a product of sum, but they are not max terms, not even one of them. All of them are not max terms. So we need each term to be a literal plus a literal plus a literal, the three letters, x, y, and z. And we have then the combination, maybe x bar, y bar, or y, z or z bar. So let's start by the first one, x bar plus x. This is basically equal to 1. So just, we can remove it. The second one, x bar plus y. What we need here, we need z. So add z bar. Remember, with the main term, it was x. If we have x, it will be x dot y, x bar dot y. Then we multiply by z plus z bar. Here we do just the opposite. So x bar for y, then we add z bar. Then we take this term x or y and distribute it over z and z bar. Distribute over z and z bar. So this will be equal to x bar plus y plus z, then x bar plus y plus z bar. This is also done here. Z or y, let's call it y or z. Y or z, just because you know it's good to have the order x, y, z all the time. Then we add what's missing, which is x, x bar x. Then we distribute y or z over x bar and x. So I will just write them in order. So we have first x bar or y or z, then x or y or z. The third term, this is done. Now the fourth one, x or z, add to it y, y bar, distribute this over these two. So we have x or y or z. Again, I am writing in order. Then x or y bar or z. Okay. Now if should be the product of these sums, these six sums, these two, these two, these two. But remember, x dot x is just equal to x. So first search for the repetitions and write them one time. So do we have other x bar or y or z? Yes, we have. This one and this one are repeated. So just write one of them. So x bar plus y plus z. How about x bar plus y plus z bar? This is a unique one. So just write it x bar plus y plus z. How about x or y or z? Yes, this is also repeated here. So just write it one time. X plus y plus z. And just finally, the final one should be right as it is, since there is nothing more to compare with. So this is f. Now let's represent them as product of sum. I mean, write the corresponding max term for each one of these sums here. So x bar, remember, x is 0, x bar is 1. Same for y and z. So this is basically 100, 100, which is M4, M capital 4. 01, this is basically, yeah, z bar here. This is 1, this is the guy here. So 1, yeah, 101, M5, M capital 5. Then we have XYZ, this is 000, which is M0, that's right. And finally we have 010, which is M2. M4, this is M5 here, guys. M5 is M5, M4 is M4, M2, M2, M0, M0. Okay. That's basically how, you know, to convert any functions that you have, into a product of max term or a sum of min terms. The core idea here is to convert any function into a product of sum or sum of product. You may have a function as a product of sum, like this one. I'm sorry. You may have a function as a sum of product, like this one. This is a sum of product. The main trick here, or the main step, or the main skill that you should learn is to convert this sum of product into a product of sum. This should be converted into product of sum. And why we did this? Because the requirement for this question is to convert this f into the product of max term. We cannot do that directly. We should first convert the sum of product into a product of sum, then this product of sum into product of max terms. One may say why we have this in the first place. Okay, if you have a circuit that has many outputs, okay, it's good to have all these outputs in the same shape, same expression, same, you know, same formulas, we can say, same shape of the formulas. So all of them either product of sum, or all of them are sum of products. If you have mix, you need to convert some of them to the others. Okay. Now, the second question that we asked in the start, why basically we need this sum of product or product of sum? And the answer is that the ensure us a low delay or less delay implementations. Okay, so if you implement your function as a sum of product or a product of sum, this will ensure you, a low delay, very low delay. Okay, let's have an example to explain why such case. So let's have two examples, F1 and F2. F1 is sum of product and F2 is product of sum. Let's start by the sum of product. Let's implement it. Okay, this is the sum of product. So we need y bar. We need another term, which is x and y. So we need AND gate for this term. We need another AND gate for that term. Then all of them will be just input to one OR gate at the output. So you always have two stages or two levels. This is level 1. And level 1 in sum of product forms has a number of AND gates equal to or less than or equal to the number of terms that you have. So the number of AND gates is less than or equal to the number of terms you have. Then in level 2, you have OR gate. This is level 2, you have one OR gate. You may have 1 million terms, but all of them will be inputs to one OR gate. Of course, assuming that you can have an OR gate that has a million input as a circuit. I mean, circuit that has million input. So this is a practical consideration. But theoretically, you all the time have two levels. So basically, what does that mean is that the signal needs to cross two gates or to experience only two gate delays in order to get to the output. So assume that at the same time, we put here values for these inputs. So these 5 inputs here need 2 gate delays to get into the output, or the output will change in response to that change after 2 gate delays. How about product of sum? Same concept. We have 3 terms here. So we have the first level here, level 1. It has OR gates and the number of OR gates just less than or equal to the number of terms of the function. Then level 2, 1 AND gate. And that's it. Let's put that into action. Let's compare it with, if you have just a function, f3 equal to such expression, AB plus C ANDed with D or E. If we blindly, implement it, it will be like this. We have here 4 gates. 1, 2, 3, 4. But look now at the delay of F3. So if at some point we put values here at A, B, C, D, and E, F3 will change in response to the inputs after 3 gate delays. So F3 here, so we need 3 gate delays, of course assuming that AND and OR has the same delay, so that F3 changes in response to the output, to the inputs. Or let's say the F3 will change after 3 gate delay. That's simply F3 will change after 3 gate delays. But with a simple trick, if we change this into a product, sum of products, and this trick is just, distribute C over D and E and or E. So AB, then CD, CE. This is a sum of product. You have here 3 terms. Each one needs an AND gate. And then at the output we have 1 OR gate. So again we have 4 gates. But if we look here, F3 will change after only 2 gate delays. So F3 here will change after 2 gate delays. This is 33% less than the first circuit. And that's basically the advantage of sum of product or product of sum. This is a standard form to represent functions. And it has benefits. It's easy. You just look at the truth table, look at the ones, look at the zeros, and that's it. Then if you do that, even without extra minimization, you are sure that you will get 2 level, which is very good. Maybe if you do minimization, you will end up with such thing here, with 4 levels, or I'm sorry, 3 levels. Level 1, level 2, level 3. But here we have only 2 levels. Level 1, level 2. Okay. So that's basically, the story of the standard form, min terms, max terms, how to express functions as sum of a product of sum of min terms, product of max terms, how to change a function or turn a function from a sum of product into a product of sum form, or vice versa, and why we need it. Basically to get less delay or faster circuits, we can say. Okay, guys. So in the next video, we're gonna continue with more properties for Boolean functions. So stay tuned. Have a good day. Bye-bye.